Good morning, ladies and gentlemen. Thank you all for coming and welcome to our webinar this morning on turning your water quality data into management knowledge. My name is Carin Bosman. I've been working more than 35 years in water governance and in water quality management. I started my career working in a laboratory and ended my career working with the prosecution of people who do not meet their limit values and standards. So I've been through the entire process of monitoring, and it's my privilege and pleasure to talk to you guys today about how to turn your water quality data into management knowledge. Some very clever people said, to measure is to know, Lord Kelvin. If you cannot measure it, you cannot improve it. And there's people who have coined these phrases, cliches, what gets measured gets done. People, if you build a house, they will tell you measure twice, cut once. And measurement is not management, but measurement is what we need to manage. What you cannot measure, you cannot manage. And what you cannot manage, you cannot change. Unfortunately, in South Africa, we have the situation that managers are often not qualified as scientists and do not understand the difference between a second and third decimal and the significance of that. And they don't understand what it is that they want to measure. And if they do measure, they have no idea how to interpret the measures or what to do with it. And this smart guy, Russell Alcoff, said managers who don't know how to measure what they want settle for wanting what they can measure. And that means we are measuring, but we are not managing. We are measuring what we think we can measure, and we spend a lot of money on expensive measurements and have no idea how to turn that into management knowledge. And it is impossible to take good water governance decisions without good water monitoring programs. To improve the water quality in our resources and our potable water supply systems, we need to know what we are monitoring and why we are monitoring it. There's a hierarchy. Information that was a sample taken and a lab result, that's data. That is not information. From data, if we can grasp the relationships between where we collected the data and why the data was collected, that becomes interpretation, and that leads to information. If we can grasp the patterns between what we see, that becomes knowledge. And once we grasp the reasons for why we see these patterns, then we develop an understanding. And then we can understand the principles behind it, which gives us the wisdom to take good water management decisions. And I would like us to move in South Africa from merely collecting data to actually interpreting the data that we collect into wisdom that leads to good management decisions. This is typically what managers would get as a result of somebody sitting and collecting a lot of lab results and putting it all in an Excel spreadsheet. This is not information. No manager that doesn't have a scientific background, and most of them don't, will be able to take any informed decisions based on this. This is not information. This is merely data. Data is values collected by measurement. But management decisions should be based on information. And information is data that has been evaluated and interpreted in the context of its collection to indicate the state of environmental, or in this case, water resource conditions. The quality of the data is a direct determinant of how good the information is, and how good the information is directly determining how good the decision is. If we have faults in our data, if our data is patchy, if our data is unverified, or there's no quality control on the data, then the decisions will be bad. But if there's good quality control on the data, if there's interpretation of the data, then the decision making will be good. It doesn't help that the computer says Intel inside, but the person sitting outside behind the keyboard have no idea what they're looking at. So what we're going to talk about in the next hour or so are all related on how to turn your monitoring data into management information. Starting with what is monitoring exactly and the cycle and process of monitoring. Then defining the purpose of monitoring, understanding the management questions that we need to ask ourselves to design and develop good monitoring programs. Touching on some pitfalls in water quality monitoring program implementation, aspects that we need to consider in the program design with relation to locations, variables, and frequencies, some sampling method and technique pitfalls, and then data management and storage aspects. Once we've collected the data, we move over to interpreting the results into management information, looking at aspects such as against what do I measure my data? What is my yardstick? Compliance specifications set by government agencies, what are correct and good compliance specifications? And then once you have compliance specifications, you can visually represent your data in comparison with these compliance requirements. This brings us to the last step, and that is how to report for management and for decision makers, how to report monitoring information to non-specialists, and using digitization and digitalization tools to be able to do that. And then there will be a question and answer session at the end as well. So what is monitoring? According to the clever people in academia, they define monitoring as the systematic collection of data for a specific purpose. For example, on certain aspects of the water resource, it's quantity, quality for variables, certain variables, at certain locations in a specific area or catchment or aquifer system, at an appropriate frequency, which is measured for the correct variables that tells us and answer the questions we've asked, which will ensure as adequate and complete as possible record regarding the resource status. And this must be done cost effectively. If you have all the money in the world, you can take a sample every day, every hour, every half an hour, in fact, and have it analyzed and send it to laboratories all over the place. But unfortunately, monitoring costs money. So you have to optimize your monitoring network so that it is a cost-effective data collection mechanism. Not only the collection of data, but also the organization of this data into information, which we need to interpret it into knowledge that can improve the decision-making process, both directly for the management of the organization, as well as indirectly to inform government, the public, and other parties and stakeholders. They want to know as well, how well are you performing, how well is the water resource performing. This little flow diagram outlines the process of water monitoring. If we take water samples and analyze them and interpret them over a period of months, years, and decades to determine how human activities affect water resource conditions, and we should present this data we collect in a format that can be understood by non-specialists. So it starts off with, let me just get my pointer here. There we go. It starts off with designing your monitoring program and taking samples at the predetermined locations in streams, dams, boreholes, pollution facilities, wherever it is that you want to take this sample. When you take the sample, it's not simply a matter of going and skipping, grabbing some water with a bucket, because this is where the accuracy of your data starts. If you collect your sample in a bad way, you are not actually sampling the water resource, you are taking samples of something completely different. Therefore, field sampling is as important as lab results and analysis. Once the sample is taken, it's taken to the laboratory for analysis, where they can do chemical tests for inorganic, organic, and radiological contaminants, as well as microbiological contaminants. Once they've done their analysis, they will provide the data in a report, and this is where the turning data into knowledge process starts. And the first step of that would entail the quality verification of the quality of the data. Are there any outliers? Is it inconsistent with what is expected in the area? What is the data quality? Tell us. And then you only use the data that passed the quality control test to visualize, interpret, and report your data. And that is then done in appropriate graphical way and should be interpreted by a water chemist against appropriate and applicable water quality criteria, which should be summarized into an interpretation report. This report can then be submitted to authorities, to the community, the public, and presented for decision making on water management measures. And often these decisions can influence and feedback into the design of your monitoring program and say, well, we didn't take a sample there, we actually need a sample on that stream as well, because otherwise we can't make a proper and appropriate decision. So this process of water monitoring is the building blocks on which the entire system is based. Now, why do people take water samples? Two main reasons. It's required by authorities and customers or the community outside your organization, and it's aimed at determining the impact of your activities on the water resource so that you can take decisions on how to change these activities, or even if it is necessary to change your activities. Now, what currently happens is that the laboratory results are sent directly to customers and authorities in large sheets, those Excel sheets, without any form of verification or interpretation. Unverified data that has gone through no process of quality control, are then used to take legal action to prosecute people for pollution. But if they use the wrong standard to compare your data against, that is not pollution, and you can't do that. And unverified data are also used to deny a product of service. I'm not going to show you the data sheet again. I showed you that already. I want to show you, for example, come on, let me just turn that thing off. Example of a graph with a spike looks like that. You can see how a spike changes the entire interpretation. Now you have to ask yourself, when you do quality control, was this once off over a period of 10 years, one high result? Is that a problem with the sampling? Is that a problem with the laboratory results? Or was that actually a problem in the resource that happened on that day, 16 July 2015? Or can we throw that specific measurement out of the data set and then interpret the rest? Because you need at least 3 data points to be able to interpret 3 samples. But if you have a large data set such as this one, which shows consistency low values except for one outlier, then you can with confidence say, but that outlier is not a representation truly of what is going on in the water resource, and therefore we can dismiss that one point. There must have been some kind of error. And that's what we talk about when we say we clean our data. Now you have to be able to scientifically defend each and every data point that you included or excluded out of your system. That type of data cleanup doesn't happen because there's no interpretation of water monitoring data. It is generally seen in a negative light, and it's not used to properly inform decisions on better water management and governance. Let me just get to the next one. In reality, therefore, our process of water monitoring looks like this. Yes, people have monitoring programs. They send people out to take field samples, send their samples to the laboratory, get the analytical results, and those analytical results are sent directly without quality control, without determining proper limit values, and without any proper graphical interpretation, straight to decision makers and to communities. And this is why people are so scared of engaging with communities, is because the communities don't understand what they're seeing and therefore have no idea and are getting upset because it makes no sense. And they saying, you guys are talking over our heads, etc., etc. And this is our current situation, why we have poor monitoring, perceptions of monitoring and poor decision-making coming out of it. Spending all this money on taking numerous samples, but not actually properly interpreting our samples and our monitoring results. So the first thing we have to do, the first aspect to address, is to ask ourselves, what is the purpose of our monitoring? And monitoring's main and primary purpose is to generate the collection of management information. that will help us to set management objectives and to develop management strategies and to make informed management decisions. And then we monitor also determine if we are meeting these management objectives. Are we complying with our legal requirements? We can forecast what ifs, what will happen, what is the trend lines looking like, and it can act as an early warning system. We also use monitoring data for things like project management, program evaluation, and policy development. We've done an impact assessment, we've made certain predictions in our impact assessment, and now we have to monitor to determine if those assumptions and estimations are in fact correct. Monitoring eliminates uncertainty in research. It can refine our assumptions and collect data for modeling, which can give us better ideas or predictions or projections of what will happen in the future. What further research are required, and have our models been calibrated correctly. This all leads to better management of the water resource. Now we can describe the monitoring cycle as follows, where you formulate your management question and set out your monitoring objectives as your first step. Then define the information needs that will address those objectives and design the monitoring program in accordance with that. Implement it and collect your data and store it appropriately. Interpret your data into management information. Present and disseminate and communicate the information, which leads to changes or improvements in your management questions and in your monitoring objectives. The bottom line, the crucial, most important part, therefore, of any monitoring program design is to understand and determine what is the management question and how can the monitoring of water answer this question. Here's an example. A guy asks, how big is the tower? And he gets the answer from his researcher, perfectly correct. The surface area is 70 squares made of 80,000 red bricks, size 5 by 5 by 10 centimeters, and what. So he's answered the question the manager asked. But if you don't ask the right questions, you won't get the right answers. If he's changed his question to, what is the height of that tower in centimeters? Because we need to monitor and look at possible land subsidence. Changing the formulation of your question, change the answers that you are getting. Now the guy can say, I've measured it with 2 different methods between fixed points, and the height is 2625 plus or minus 0.5 centimeters. That answers the question. Why? Because the manager said what he wants to do with the information. We want to look at land subsidence. Why is land subsidence important? Well, if the land falls underneath the tower will fall and people can die and can kill people. So asking how big is the tower does not include the reason why you want to measure the tower. Including the reason why you want to measure the height of the tower gives you a better answer and can give you the correct answer. Sorry, there are many threats to our water supply in urban and rural areas, both surface and groundwater. And groundwater is one of the most poorly understood components of the water resource. And people have boreholes all over the place, but they don't even know if the borehole is in the same aquifer as where their impact is. I can have a borehole over here trying to measure this leaking storage tank, but it won't measure that leaking storage tank. It will measure this in situ sanitation because of my flow direction of my groundwater. If I don't first determine the flow direction of the groundwater, I cannot establish a groundwater monitoring program because I need to know where am I measuring what. Early warning systems, especially when we use groundwater for community water supply, we need to both understand the groundwater flow direction and how deep our contamination might or potential threats might happen. And therefore we will have boreholes that will tell us it's a defensive detection monitoring, how far am I from my abstraction borehole. In offensive pollution monitoring, there's a potential source, This one is a background and tells you what it should be like. This one tells you the impact of this potential pollution source. So you can see there's all different kinds of reasons and motivations why a certain borehole or monitoring location should be established at a certain point. You do not only look at quality, but also at quantity, but also at quality. And detection of groundwater quality trends in aperture replenishment in the vicinity of a public supply well measured here shows you that the milligrams per liter of nitrate, which is an indication of a potential health risk, shows that it was quite stable, but the more we started pumping, the shallow monitoring boreholes showed a significant trend of increase. And this gives us an indication that over time that will percolate down from above and impact our deeper aquifer, which now is also starting to show an increasing trend. Therefore, the shallow monitoring of nitrates in this case gives us an indication of the potential threat to the deeper aquifer used for the community water supply. And you can therefore use your shallow monitoring as an early warning of potential threats to the aquifer and groundwater supply quality, which now tells you we are going to have to put in some type of nitrate removal somewhere in the future for which we need to budget. And there you can see the management decisions coming in. Determining potential threats to aquifers and groundwater quality is a critical requirement for detecting any threats to groundwater potable water supply for the communities. We must therefore properly design the monitoring network that relates to the spatial variation of groundwater flow and flow direction and recharge. How do we determine the management question? How do we establish what is it that our monitoring network should do and how we should design it for? And this slide is probably the most important slide of this entire presentation, because these are the questions you need to go and ask of your management and tell them to put on a hat as a financial director. So put on the hat, what are you? Financial director, environmental manager, community member, counselor. What is the role that you play? Because all these different roles have different expectations from your monitoring program and will have different information needs. What would these people like to know? The financial managers need to know or expectation is different from that of a community member. The compliance manager would say, I would like to know whether we comply with water affairs specifications. The community member would say, I would like to know whether the water I drink is safe. And then the reason for. So remember that picture of the tower? So that we can determine subsidence, so that I can determine how much money to spend on the treatment of water, so that I can determine whether I need to buy water for my kids. All these motivations are the management components thereof. And you can see how different stakeholders would have different information needs and different motivations for each of those information needs. So if you haven't done this already, go and ask yourself, why are we monitoring groundwater quality at this specific point, and what is the information it's telling us? Or why are we taking a surface water sample at this specific point, and what is the information that it's giving us, and what is the management question that monitoring that specific point? What is the exact management question taking a sample at that exact specific point is answering for you? Key questions and considerations in this is, what is the purpose of the information you want to generate? What is the management question that this expensive monitoring should be answering? Then, where should we do it? At what frequency? For which parameters? And are there any specific sampling techniques associated with the type of sampling location and with the type of variables that I want to analyze for? Because I can't take, for example, a sample in a plastic bottle and send it for organic analysis. That sample would be completely flooded with the plastics that's now dissolved in the time that you transport it from the sampling point to the lab. So you have to change your sampling containers even depending on the type of analysis that you would like to have done on the sample. Then, what kind of analysis? What are the variables? Why are we looking at cyanide if our factory uses no cyanide, produces no cyanide? There's nothing near us that has any cyanide. Why should we have an analysis done for cyanide? Another company who might use cyanide in their extraction processes, yes, they must sample and analyze for cyanide. But a company who doesn't touch cyanide, who hasn't had produce anything that is related to cyanide, really don't need to analyze for cyanide. And that saves money again, which is a management benefit. Then, how am I administering and managing my data? How do I store it? How do I keep record of who had done what, when, and where, and wow. Once we get to our data all collected from the laboratory, now we need to interpret it, make applicable graphs, and compare against applicable and appropriate limit values, because that tell us, are we complying with government specifications? Or we need to get concerned because we are exceeding an early warning system. What is going on? And limit values is super critical, and there are different types and ways of setting these limit values. After interpretation, then it can be reported to non-scientists or non-specialists and communicated to stakeholders who can then take these decisions, or who can understand then what the implications are of this monitoring exercise. Last step is to give feedback to management around the design of the program. Yes, the sampling locations are correctly and the correct sampling points. No, we need to add this variable. No, it's no longer necessary to analyze for these and these and these variables, and so on and so forth. So for monitoring programs, there's 5 primary considerations. What is the purpose of your program? The business objectives, your proactive approach, and how accurately do you require this measurement to be? The budgets and costs associated with implementing. The more sampling points, the more expensive the program. And the more variables, the more expensive the analysis. The more frequent, the more expensive the program. And here you will also consider economies of scale. And optimizing the design of your monitoring program means selecting monitoring locations, frequencies, and variables that will answer as many management questions as possible. If I can get one location that will answer the questions of both my company manager and the community outside there, it means I can only have to sample once and get 2 different types of decisions out for 2 different types of decision makers. And that's monitoring program optimization. Taking action on your monitoring information. What is the problems that you potentially expect in your monitoring program implementation? And then feedback of that into management presentation. Also looking at existing monitoring programs of yourself and of other people, and dealing with historic data. Now, dealing with historic data is very, very important, because people have been sampling before you. We've even had samples taken in the 1960s in one of my places in Natal, which gave us extremely valuable information. Data is expensive to collect. You never throw it away. You always keep it. You might put a question mark over the validity or the accuracy if you were not involved, or if there's something strange looking around it, or if there was no data verification done, but it's still valuable information. And the longer back your record stretches, the more assurance you have in that your monitoring program is good. So don't throw away the data collected in 1980. Keep it, and keep it in your graphical representations, because it tells a story. It's a snapshot, a photo taken 20, 30 years ago, which can still have valuable information today. And then lastly, interpreting the data against correct standards and limit values. And I cannot stress this enough. I see so many times laboratory reports coming out with the results of your sample on the one side and the drinking water standard on the other. Now, ladies and gentlemen, it is completely scientifically incorrect to compare especially groundwater, but also surface water, river water, against a SAMBS drinking water standard. That SAMBS drinking water standard is designed for a specific purpose. It is what water that has been treated at a water purification works should comply with. It is not what water coming out of the ground or being in a river should comply with. In fact, if you compare river water to the drinking water standard, you are actually saying, well, much of the water in our rivers are of a much better quality, and you will not meet ecological quality requirements if you simply use the drinking water standard to compare river samples against. Similarly, groundwater. Much of our country has got very impressive geology, and I'll show you a geological map just now. In certain areas, the natural background arsenic levels are way, way above what is suitable for human consumption. The only time that it's acceptable to compare groundwater quality against a drinking water standard is if you want to use that borehole's water for community water supply, and you need to determine, do I need to apply any treatment to this water before I can supply it to a community? Using incorrect and inapplicable and inappropriate standard to determine compliance can lead to serious legal liabilities. Think like a specialist, like a scientist, and not just do it like a parrot because everybody else do it. Water quality changes on a site-specific basis. In every river, the Waterfall River has got a different water quality than the Sabi River. And so aquifer in the Table Mountain group of rocks will have completely different background quality to groundwater in the Barberton greenstones. Scientists must develop site-specific limit values to compare results again. And don't tell me, I know we have resource quality objectives. Resource quality objectives are set for a specific water resource at 4 or 5 resource compliance points over a river that is 300 kilometers long. That's not site-specific. Site-specific limit values must be developed. And if we do that properly as scientists, we will not get strange things in our licenses. For example, that you must comply with the drinking water standard at your PCD. Or, like I've seen, that the sulfate concentration in your pollution control dam must be 0 milligrams per liter, which is completely scientifically incorrect. Why would you build a pollution control dam for water with a 0 milligram per liter sulfate content? Makes no financial or scientific sense whatsoever. Remember to think like a scientist. You must always offer evidence to support what you do, to support your statements, and to support every decision taken in relation to your monitoring program. A good monitoring program has got correctly identified, located, and described monitoring locations that is being visited and samples taken at an appropriate frequency, where you ask the laboratory to analyze for critical constituents as well as some additional constituents for assurance or insurance. Now, insurance is something you might not ever need in your life, but as the daughter of somebody who sold insurance for life, I can tell you that if you, for example, have a community that says, oh, but you're poisoning our water, and you've never done an analysis for the heavy metals, you have no defense to say, but it's not me. But if, for example, you've taken that analysis once a year and checked all the heavy metals, then you have the insurance to show up the scientific evidence that can say, look, no, it's not us. Here is our annual analysis for heavy metals. It can't be us. And that's why I call constituents for insurance. You might not have cyanide at your factory, but sampling on analyzing once a year for cyanide won't hurt anybody, won't be so expensive. I'm not saying sample for it every month. I'm saying once a year, once every second year for insurance. That if someone comes and says, oh, but you put cyanide in the water, you can have the evidence to back you up and say, it's not me. Also then looking at the completeness of your records and how you keep your records and have your data audited. Then processing this data into management information by using the correct applicable standards and present this data in an understandable way, which can communicate to non-specialists. Now, if that's what a good monitoring program should look like, where are the pitfalls? Where's the problems? And I'm highlighting just a couple in terms of this cycle to show you things that you should be careful of or watch out for. And the first one relates to a poorly designed monitoring program. If you sample simply for the sake of sampling, and not design your program to answer management questions, you'll have a whole bunch of monitoring locations, but they might not really be relevant to any management question whatsoever. Sampling them at incorrect frequencies and analyzing for incorrect variables will mean that you have a lot of data generated, but you cannot do anything with it. You've just generated data for the sake of data collection. Then, using incorrect sampling techniques. If you use certain things that's continuous monitoring, you have to consider aspects such as silting, vandalism, theft of your instruments, and incorrect flow measurements. That means if you want to do salt load determination, you have to measure flow as well. And now you don't have a proper flow measurement, which means you can't properly calculate your salt loads. Laboratory inconsistencies is another pitfall. Laboratory inconsistencies happen often, more often than we think. And although the lab might be SANAS accredited, things still go wrong. And this is why you always have to include what we call double-blind samples, where you take a split sample of the same place and send it to the lab under two different numbers. That makes sure that if the lab then doesn't come back with the same results of that split sample, then there's a possible problem in the laboratory. So do that at least once a year, where you do double blind or split sampling, sending two differently labeled samples that comes from the same source for the laboratory, just to check up that the laboratory has consistent results coming out of it. And then the biggest one, the poor interpretation of data, or the non-existent interpretation of data, where incorrect standards and guidelines are used to determine things like legal compliance. So how do we design the integrated monitoring program? Consider your potential impacts. Where is your source coming from? Remember the slide I shown you with the offensive early warning versus defensive early warning? Why is that sampling location there? Have you sampled at the same places where you can look also for things like biodiversity? It makes great sense to have the same sampling location for surface water as your biomonitoring survey sites, because that will give a very good indication of why you see certain things. And then develop an integrated monitoring program where one location can be used to answer more than one management question. Arrange to maximize commonalities between management questions that can address multidisciplinary or cross-cutting questions, and that can be used for modeling as well. Also remember that water is the driver of, for example, aquifer contamination, and you have to identify sources and pathways from where your source of pollution can hit your water resource. And this means you need to look at things like a site water balance, which looking at all your different sources of water, where is it being captured? Where is it being used? Do you have any converters like treatment works? Where is it being recaptured? Because now remember, this is dirty water, and each of these recapture facilities might contaminate groundwater. And then where is it sent back into the atmosphere or into the environment? And each of these things would tell you, oh, I need to sample downstream from this, downstream from this. I have to sample in this stream and this stream. So the first step that you do in designing a water monitoring program is evaluating your water balance. Once you've identified where, then you're going to determine how often. And there's two frequencies, both frequency of sampling, taking a sample, and the frequency of analyzing for certain variables. Now here you've written down all your components, what sites will measure impacts from those components, what are you measuring at those sites. always the level for groundwater, and then your macrochemicals, that's your major anions and cations, will in this case be quarterly, and heavy metals also quarterly. At the waste rock dump, levels monthly, macrochemicals twice a year, and your heavy metals once a year. You see how cost effectively that is now designed. And if they dewater, levels is monthly and only one sampling point selected because it can answer multiple management questions on a quarterly basis. And this means we've optimized our monitoring program. You have to choose critical control points. That Pareto principle of 80% of the effect with 20% of the effort. The biggest effect of the least effort, if you can select one or two monitoring points that will answer a number of management questions, then you've optimized your monitoring program. And also look at the spatial distribution and statistical significance of your sampling frequencies in terms of your geological or hydrological units, as well as the dynamics of the system and of the parameter. This gives you an idea. It's a schematic representation of a facility in Natal where you have a number of streams coming together, and on each of these streams there is a certain impact. Now I can simply take one sample there, but taking one sample here will not tell me what the impacts are of these different facilities. So there's a new shaft at the back here, which means I have to take a sample for background upstream from this shaft. And then there's an old mine. The impact from this new shaft must be measured before the impact from the old mine starts playing a role. And then after that old mine, I have to take another sample. And the difference between what is in this sample and what is in this sample and what is in this sample will tell me what is the impact from here and what is the impact from here. And so you can see each and every monitoring point on this set of streams has a specific role to play and a specific question that it answers. Your monitoring location should be optimized and should be practically selected with practicality. It doesn't help I say now the sampling location is 2 kilometers away from a road, because the person you send out to take a sample is going to just park the car on the road and take the sample right there. Unless there's a very good reason why you should walk 2 kilometers through the bush to go and take a sample, select the sampling location at the road where it's easy to access and easy to take the sampling. The sampling locations will depend on what is the purpose of the monitoring program and the management question asked. What is the accessibility and physical constraints on the site? And how is it influenced by high and low flow conditions and other nearby activities and so on? You have to also consider geological considerations. You can't just drill a borehole here if you want to measure impact that's happening on this type of geology, because there will be a different type of aquifer. And our geology can get quite complex, so that if you have one factory facility over here that spans 2 or 3 or even more, your monitoring program has to be designed to measure the different aquifer systems. You also have to consider topography, because water flows. So if I want to measure downstream, I have to first look at what is the flow direction. This will be downstream and this will be upstream. I once saw a report where people had the flow direction of the Vaal River incorrect and labeled the sampling points incorrect, and what was actually the downstream point they labeled upstream, and couldn't interpret the results to save their lives, because upstream always came out better quality than downstream because they labeled it wrong. This gives you an idea of how the topography can influence. This facility is on a watershed, which means activities here will influence that stream, and activities here is going to influence this stream. So it doesn't help I sample in this stream for things that I expect coming from this area here. The water will flow in that direction. And it doesn't help I sample for variables of things I use on this side in this stream over here, because the water is going to flow in this direction. You must therefore look at all your site-specific considerations in the design of a monitoring program and say, all right, a sampling point here will measure what's happening here, but not what's happening here. And a sampling point here will measure what's happening here, but not what is happening on this side. For groundwater, you need to look at the levels, the depth, the flow rates, and the background quality. For surface water, you need to look at the flow rates and of quality, and you have to also consider your meteorological data. Moving over to how to sample, there's an entire series of SANS standards which gives you guidance on the design of sampling programs and on sampling techniques for specific things in water quality sampling. Get hold of these. There's about 13 of them. And there's different sampling techniques for different sampling substrates. And you have to make sure you understand and your samplers understand this. I rarely see people reference this SANS 5667 series of standards. Water consists of molecules, and the macrochemistry and the microchemistry and the radiochemistry, dissolved gases, organic compounds, and biochemistry all plays a role in the composition of a water sample taken at a specific location. You need not understand everything, but you need to understand, when do I actually look at radiochemistry and radioactivity? Is it actually necessary? Do I need to look at things like dissolved oxygen? Do I need to look at organic compounds? And not just looking at the macro and microchemistry, which is your major salts and your metals. Also look at things like organic compounds as well. So when you design your monitoring program, you need to understand where are you going to sample and have a given exact description of the coordinates in an accessible format. Remember, a big red bus can hit you tomorrow, and the person coming after you, they need to understand why you have taken a sample at that specific location, and they need to be able to find that sampling location without you holding their hand. So you have to give an exact description of the coordinates in a format that's accessible, like DMS or decimal degrees. The groundwater specialists, they love the XY system or mines, but you can't go and visit that if you don't have the reference point. So with our modern things of Google Earth and GPS and so on, it is actually possible to give somebody the exact location of where a sampling point is. I don't know if you've ever had to go and look for a borehole in the bushes in a 10 meter by 10 meter square. It is virtually impossible. But if you find the exact DMS coordinates, you can find that borehole again. The second question is then frequencies. When are you sampling? And then the variables, what are you analyzing for? And more importantly, why are you analyzing for that variable? And the last consideration is, how are you sampling? Your preparation, marking of your labels, and handling of your labels. And this is then how you can optimize in terms of variables. These are my monitoring locations. For the macros, I'm going to do monthly. For the micros, maybe quarterly for some. For the heavy metals, some monthly, but some only biannually. The cost, the value implication of the cost is the worth of the data. Bi-monthly or biannually, monthly, and quarterly are typically what you can use, and you can distinguish based on variables and not just on taking samples. Your frequency of sampling depends on your type of samples. Water changes about every 2 weeks in a surface water body. Therefore, taking a sample once a month is an appropriate frequency for a surface water body. Groundwater, if you have slow recharge, taking a sample twice a year is completely adequate. You don't have to take monthly groundwater samples. But if you have a quick recharge, or you have an active, close contamination zone, or you're giving community water supply, you might need to take a daily sample of your borehole because you need to assure the quality of the water provided to the community on a daily basis. Grab sampling, which means go out and grab a sample once a month, versus continuous monitoring. Now, this is an example of a continuous monitoring station which takes a reading of EC, electrical conductivity, and temperature once every 30 minutes. This is very important when you do things like salt modeling, salt balance modeling, and so on, and it's done for a specific purpose. What is the salt load entering the Vaal River on a daily basis? And that was the reason why this monitoring program was established. However, if you do something like that, there's a whole lot of considerations. Your probes might silt up, and then you are no longer measuring the salt in the river, you're measuring the salt in the silt around the probe. And it needs regular maintenance, because if you don't regularly maintain it, your accuracy goes down. We've had somebody who said, no, but we can measure connectivity up to a third decimal, but it's not necessary to measure connectivity up to a third decimal. Measuring it up to 1 decimal was completely sufficient for the purposes of the program. So depending on what is the needs of the program, the management question once again will determine what is the cost that you have to spend on your instrumentation. Technology changes monitoring, and we can see more and more things like real-time monitoring on water levels and internet-based databases with real-time reporting and smart algorithms to do things like trend analysis. This all contributes to giving proactive feedback to our customers, including the managers. The next step now in our monitoring cycle is looking at data collection, different types of sampling techniques. The photo that you see there is me taking a sample in the Kokemoerspruit, and you will always put your sampling bottle in the downstream, so flow direction will always be from this side, and your hand is out of the way so that your hand does not contaminate what comes into the sample bottle. And you have to make sure that you understand why you take a certain sample. There you see I'm taking a sample in a glass bottle, and that is for microbiological analysis and organic analysis, and not for macrochemistry, because glass bottles are inert and will not interfere with the laboratory results. There's a whole, again, this SANS 5667 series of standards that gives guidance on sampling techniques at a range of various sites. For surface water, groundwater, and soil samples, and for different types of organisms, there are different types of sampling techniques. Groundwater monitoring requires special sampling procedures, and you need to know what are you looking for, and that influences the sampling technique. For example, well pumping and sample handling may cause major sampling modifications through air entry, degassing, and losing volatile organic carbons and compounds. And therefore, you must understand what am I going to sample for. You won't purge. Purge means pumping the volume of a borehole 3 times out. You won't purge if you want to see if you have volatile gases, because if you purge, the volatile gases will all be gone. But you will purge if you want to see what is the actual contamination or concentration in the aquifer, and you have to then capture this information. What have I done when I took the sample? Did I purge or didn't I purge? For how long did I purge? And so on. For example, a stratification in aquifers affected by AMD always happens, and that the deeper you go into the aquifer, water has settled out. Salty water is heavier than fresh water. So the deeper you go in the aquifer, the higher the salt concentration will become. If I now purge this aquifer, I won't get these readings. In this case, therefore, there was no need to purge the aquifer, because I actually wanted to see, do I have salt stratification going down? This is my conductivity after purging. In other words, I pumped the whole aquifer out. This one, I did not purge, and therefore I can actually see the stratification of salt as I go deeper down the borehole. Now, in this case here, the lady is taking a sample at the borehole, but there's no way of telling what is she actually sampling. And if you look on there you see some algae in the standing water. There's a shimmer of oil over there. So is she sampling the aquifer, or is she sampling the water that's standing around that borehole location? And capturing that information is critically important when it comes to the interpretation of some weird result that you now get from the laboratory. The importance of recording field conditions during sampling cannot be underestimated. Field conditions must be recorded because that field conditions is what gives us the information when we do quality control and we get strange results which we now have to interpret. And it starts there in the field. Next, also important point to highlight is to make sure that people who sample does so with safety. This gentleman over here is sampling in a highly unstable tailings dam that had been eroded, and there's acid mine drainage running out of this with a pH of 2, and he has no safety shoes and he has no safety gear on, which means that acidic water can burn his hands. And that has got a serious implication and a serious health liability associated with that. So you must make sure that if you send somebody to take a sample in something as corrosive and abrasive as this, that you equip them with the right safety equipment and safety gear. Also related to sampling that plays a big role in interpretation of your results are your preservation techniques. If you want to analyze for certain variables, there are different preservation techniques associated with each type of variable. And here SANS 5667 gives us guidance on the preservation and handling of samples. Different types of bottles for inorganic, organic, or bacteriological samples. And here your field notes, in fact, what you've done in the field are critically important. If you've taken the organic sample in a plastic bottle, your results will be completely unusable and uninterpretable. This is just a tip of a summary for these determinants. This is the type of procedure. That's the type of sample bottle. And here you see organics, TOCs, and so on, must be dark glass or Teflon. This is how long you can store the sample, and this is how difficult it is to do this. And all of this has to be written down in the design of your monitoring program. Getting to sample analysis, we also have a prescribed methods to be used in SANS 241. From aluminum to manganese, all of them have different prescribed test methods that should be followed. And these are the methods that a laboratory is being accredited for. If the laboratory wants to deviate from these methods that's prescribed, they must have very good reason. And you must then note on your results that this is not accordance with a prescribed SANS method. And this deviation from these prescribed methods must be included in the data report. The format of the data is critically important. We've seen laboratories report data in grams per 100 milliliter, and then people assume that is the same as milligrams per liter. No, ladies and gentlemen, a grams per 100 milliliter needs to be converted to milligrams per liter. Otherwise, you're not comparing apples with apples, and you will have very weird results. And this is why a data interpretation step is so critically important, from getting your data to visually representing it. Now, the interpretation and visualization of data is probably the most important part of this, because now we move back to the design. What do we do with the data? What was the management question? And I see we often suffer from a data overload and information deficit, because we do not present our data in a manner that can be understood by a non-specialist. This example here is of some non-specialist who simply added in milligrams per liter all the different concentrations of a number of variables in milligrams per liter and added them together on a bar chart and said, this is an adequate representation. It is not, because the size of a sulfate molecule and the size of a potassium molecule completely differs. And you cannot just simply add them together in milligrams per liter and say, that is my TDS, because that's scientifically wrong. You have to convert, if you want to compare like that, to something called milliequivalence. And milliequivalence uses the molar mass to calculate an equivalent, and that can be used to compare. So a number of different graphs depending on how you interpret and what are the questions. Time series plots. If you want to do cation anion balance, you always must convert to milliequivalence. And for groundwater, also converted to milliequivalence, there are specific types of plots. Time series plots are very simple to construct. You simply put your concentration of your variable on the y-axis and time on the x-axis, and here you see a period of 2008 to 2011, 3 years, where a number of boreholes at community members' houses had been sampled, each represented with a different color. There is a limit value set for sulfate for these boreholes for the people, and you can see that over this 3 years, all these community boreholes were not affected at all by the mine's activities and were well within that site-specific limit value. This is why time series plots are so important, because they tell a specific story that gives you an assurance of whether you are impacting somebody else or not. A stiff diagram is used to display cations and anions in milliequivalents per liter. And remember that the laboratories will report in milligrams per liter, which you now need to convert into milliequivalents per liter in order to draw a graph like a stiff diagram, which compares your major cations and anions, chlorides, nitrates, alkalinity, and sulfates, with your cations, potassium and sodium, calcium and magnesium, on a milliequivalent scale. And here you can see that this water is high in sulfate, high in magnesium, and you can say it has a magnesium sulfate characteristic. Melcher diagrams is also similar salt balance diagrams and displays anions and cations on an 8-point star. Originally, this guy, Mr. Melcher, in the 1930s, he said on the anion side we should have carbonate and bicarbonate separately, chlorides and sulfates, and then have magnesium, calcium, sodium, and potassium on the cation side. Now you can already see that here you have 4 cations, whereas on the stiffer diagram you added them together and only had 3 on each side. Because we measure something like total alkalinity, which gives the combined carbonate count, Mr. Mike Silberbauer from the Institute for Water Quality Studies said, let's just use total alkalinity of the sample to represent these anions. And in a paper he wrote in 1991, presented this. Now you'll see these graphs on each and every one of the data sheets that has been produced by Water Affairs. Myself and my colleagues, we said, well, now we have an open space there in this graph. Let's use it for something that will tell us a story. And we then said, nitrates. We need to look at the nitrates because nitrates has a health implication. Nitrates have a significant, a lot of our groundwater is influenced by nitrates. So let's add nitrates in the empty slot, and we call them Melcher, including nitrates. And here you can clearly see the sodium chloride influenced water, a magnesium sulfate influenced water, and water with a high nitrate condition. These are particularly useful to distinguish the overall characteristics of the water resource and can be used to present it on maps. Here, all these boreholes have that typical sodium, there you see sodium chloride characters. This one is strongly influenced by magnesium, which tells us this is probably in a different aquifer system than the rest of these, which have the strong sodium chloride characteristics. And so you can represent a salt balance or a salt character visually on a map. Piper diagrams, I'm not going to talk about too long, is used for the comparison of many different samples, but only for a once-off, and shows inorganic compounds on 2 separate ternary plots, where you project the ternary plots on a diamond, which gives you a combination of sulfate chloride based on total anions and cations. You can interpret then by saying if the graph plots over here, it's a gypsum groundwater and acid mine drainage, versus if the graph plots over here, it is a sodium carbonate, sodium carbonate water, which is fresh water influenced by ion recharge. And you can see how this starts to answer management questions. The next one, expanded Durov diagram, uses two of those ternary plots projected onto a 9 blocked square. In each field of those squares, it tells you something about the groundwater, whether it's fresh, recently clean recharge, or whether it's ground that has been mixed or influenced by contamination of acid mine drainage and so on. Now, coming to interpretation, I guess I almost lost you guys with those plots. You have to make your interpretation understandable to the non-specialist. And the first and foremost thing is to ensure that you use the correct criteria or limit values. Then filtering and correcting your data is as critical as taking the sample. What happened in the field when the sample was taken? Do you have field sampling sheets? What happened in the laboratory when they did the analysis? Do you have the lab analysis sheet? Did they indicate on there that they use a SANS method? If they didn't use a SANS method, why? And how accurate is the alternative method of analysis that they use? Do statistical and trend analysis and then report the results as management information, understanding the geochemistry of the area. This is just some examples of time series graphs where you can see appropriate limit values for fluoride, nitrate as N, manganese, and then here you see manganese as N. This one is a drinking water, therefore the limit value is 0.2. This one is groundwater, therefore the limit value is 0.4, and it's adapted according to the background. And in this one you can see, well, only 2 sampling locations, that's this one, the black one, who exceeded in 2004, and currently this orange one is exceeding the manganese limit value, but most of them are way below that limit value specification. This tells a story based on which you can take management decisions. Understanding your field conditions during sampling and also then filtering and correcting. 5 different sampling locations, all of them mostly plotting in the 0.1, 0.2 area, and all of a sudden, all of them have an outlier on the 31st of July 2011. This tells me there was something hinky in the lab on that day. Something happened with the analysis, and I can filter those results all out because there's no other explanation, scientific explanation, that will explain why I all of a sudden have that spike. There's statistical methods that you can use to determine these outliers. And those of you who've heard about a bell distribution will know that statistically data will fall in a certain bell. Now, if you look at that, 50% of the data will be in that area, 25 in that area, and then the rest in those areas. If you take a picture of from the top, you will look like this. It will give you a box, and the outliers will be like whiskers on the side of the box, and that's called a box and whisker plot. Now, looking at bell curves from the top as your data for each of your data points gives you an idea of how accurate your data has been taken. And you can now plot all these different little box plots and see this one often gets outliers, but most of the time it's underneath my standard. This one always exceeds my standard, even with the lower and upper percentile, and same here. And so this statistical evaluation of my data tells me, like, for example, on this one, that point is a far outlier, and I can disregard that, but I have to consider the rest of the monitoring results. Trend analysis is what you then see, well, my data shows a downward trend, which means that I'm slowly reducing the level of water in this aquifer, and you can even plot trend lines on top of that. one can get very interesting dedicated interpretation graph. And this is an example of one called the Ficklin diagram. pH is a logarithmic measurement of your hydrogen ions, H. And if you plot pH in a logarithmic scale against the logarithmic concentration of sulfate, this is the type of diagram you will get. Should your data now plot in this range here, you can call that acid rock drainage. But you also get things like neutral mine drainage or saline mine drainage. And these things can have impacts and implications as well. That might not be acidic yet, but already cause a saline impact. And this type of graph will give you this kind of interpretation. I'm not going to talk too much about all these different factors that from a natural perspective can influence water quality. Understand this is that the mineral composition of your host rock, ground and surface water alike, the general hydrogeologic framework, and the potential for mixing can all influence the water quality at a specific sampling location. And you need to understand these geochemical influences to be able to interpret. The rock type, the relief, the climate, vegetation, and time are all environmental factors that can influence groundwater chemistry. We cannot expect the groundwater quality in the Karoo over here to be the same as there in the Barberton supergroup and the Gravelet, Pietersburg, and Kraaipan groups. The groundwater background chemistry will be completely different there, from here. And this is the reason why we cannot use a uniform standard to compare water quality results for the whole country against. We have to develop site-specific limit values. Even locally, on a local scale, in this facility over here, this is Karoo, this is Transvaal group. The background quality in this will be completely different from the background quality in this, and I have to understand those differences when I do interpretations for a borehole over here as opposed to a borehole over on this side. Understand the local site-specific conditions. These are just different reference conditions for some aquifer types, and as you can see, in igneous terrains, you expect conductivity between 30 and 350 millisiemens per meter, versus in the Karoo, you're typically expecting conductivity that exceeds 300 millisiemens per meter. And so there's differences with the Table Mountain group and in superficial support deposits in coastal aquifers and in natural surface waters, where you have rainwater in terms of the dissolved organic carbon of 0.5 to 1.5 milligrams per liter, whereas groundwater is always less than 0.5, and rivers and lake will be a dissolved organic carbon of 2 to 10 milligrams per liter. And these are natural phenomena. Trace elements, those are generally occur in concentrations of less than 1 milligram per liter. And no, they are not called toxicants. I know these guys who work with aquatic organisms loves this word toxicant. There's no such thing as a toxicant. Not all trace elements are toxic, and people need the trace elements in small amounts for their bodily functions. So you can't call them toxicants. They're called trace elements. Words have meaning. Please use the correct terminology. And we need to also measure the specific trace elements, which we need to then interpret properly. Always remember to check. Maybe you've had infiltration from above. Remember that photo I shown you of the lady standing in the pond of water next to the borehole. The last component of this is then presenting your data, disseminating the information, and communicating of the information, because now you are reporting for management decision making and action. This means you need to present the data in a way that will answer the management question, that will address that manager's expectation. And communication takes two sides. If a scientist communicates in a certain way that only the scientific community can understand, then managers and community members will lose interest in your monitoring program and will never, ever be able to understand what it implies or what the meaning is. You have to report for non-specialists. You have to describe the results and establish possible causes to facilitate management actions. Here, for example, we'll see over a long time and then all of a sudden an increase. Now, this is the part that you need to explain in non-technical terms for your managers and for your communities. And also remember that you can only interpret based on what you actually have. I've seen so many people write monitoring reports that says, oh no, all the water limits are, all the groundwater, everything is in limit values, but the mine should still line the pollution control dam. Why? On what information in your report that you base that recommendation on? You have no leg to stand on. You have no information that supports that recommendation. Your recommendations and conclusions must be supported by the data contained in the report. You cannot make wild recommendations like line the PCD if you have no scientific basis to base that recommendation on. That's scientific fraud. I'm sorry, but that's scientific fraud. Where do we take monitoring into the future? How do we make it easier? How do we make it easier, accessible for non-manager or non-scientists and non-specialists? And this is what we've done in the last couple of months. We now have Water Research Commission funding to develop certain tools that will make monitoring easier. The first thing we developed is an app called Water Monster. The WRC is funding this, which is on your cell phone, and you can collect all your field data on your cell phone or on a tablet. You don't have to fill in on a clipboard, and you can even write how long have you purged the borehole and how take a photo of you taking the sample. You submit that, you press submit, and it arrives directly in an email in your inbox saying, hi Shane, we've got a new field data collection form. And in this way, we take a lot of the slack out of the schlep, out of rewriting field data in order to make the interpretation easier. If you can automate your field data collection and get it all together in one field data form, which includes how did I preserve it, how did I filter it on site, and so on, you prevent data loss and you facilitate much easier interpretation of your monitoring results. And what it also do is if you've taken, for example, 20 different samples at 20 different locations, you get it all together at one specific spreadsheet, which will make it easier now to link up data with field conditions. The second tool that will take us into the future is the automation of graph generation. And here we've developed also a tool funded by the Water Research Commission called Lego1, because Lego1 is a water monitor and is very fast and can show you trend lines. So Lego1 make your life easier. And this is just an example of what you can get making use of Lego1. Here's an example of an interactive graph, which helps you understand what is going on and what is happening. So you sign up for the service, the graphs gets automated, and you get a graph on your browser, which you can share with the community, which you can download as an image, and you can see precisely what is happening at your monitoring location at that point in time. You can also get, for example, a dashboard, which will give you a summary of all your different water data. There is your constituent, and that's the box plot for that constituent, the minimum, medium, and average value measured at that constituent, and it was 31 samples taken over a specific period of time, which helps you interpreting your data. You can go for a little more detail on our website, but suffice to say is that we are very excited that the WRC has decided to fund this project to make the automation of graph generation so much easier. Do go and have a look on our website. That is www.cboSS.com, at our Lego One and our Water Monster tools that we've designed to make monitoring easier and turn monitoring data into management information. To summarize, monitoring is not a mitigation measure. Monitoring must be effective and cost effective. Monitoring is a proactive step. Monitoring is not management. And data must be interpreted properly before it can be regarded as knowledge. Monitoring results must lead to action, including the optimization of the monitoring program through feedback loops. And ask yourself the question, does my monitoring answer the management question that I've asked? The basic rules for a successful monitoring program, in summary, is that your design of your network must have clearly defined objectives. You must understand things like geology and topography to know how to optimize your network. And you must select your monitoring parameters and locations according to its objectives. The implementation of your system, you must use appropriately constructed observation and abstraction wells using the correct field, equipment, and lab facilities. Have a proper operational protocol and data handling system, and you must integrate surface and groundwater monitoring where applicable. Remember to check your data quality through both internal and external controls, including things like double-blind sampling or split sampling sent to laboratories, even though they are SANAS accredited. And decision makers must be provided with interpreted management-relevant reports containing graphical representations of the data. And you must, like in any other plan, do, check, act system, periodically evaluate and review your monitoring program. In that way, we can take this process of water monitoring all the way from collection of data to appropriate results communication and good management decisions. And we don't just have data on which poor managers have to make decisions on. We can actually give them an understanding and the wisdom to make proper water management decisions based on good water monitoring data. At this stage, I'm going to hand back to Melissa, and maybe she will handle if there's any questions that you guys need to ask or aspects that we should maybe highlight or spend more time for. Back to you, Melissa.
Thank you, Carin. Yes, we'll be taking the questions now.